I think so. Is it open? Yep.
Ready to go? Okay, guys. So this is the first lecture series of this year, and the idea of this was to give you a little bit of introduction to some stats, because I think we want the following lectures to kind of delve into the evidence behind certain things, so just to get a sort of a framework for that. I realized sort of halfway through this that I think we want to touching on some epidemiological concepts as well would be important, so we'll go through that maybe more the second lecture. So this is going to be a two-part lecture. So this one, the key concepts are numbered, so we're going to go through sort of types of data, some brief descriptive statistics, very basic stuff, some bias and variability, confidence intervals, type 1 and type 2 error, and comparing means. You'll see there's some sort of subheadings here. So in order to cover some of these topics, you kind of have to delve a little bit deeper into the stats. So that's why we're going to go through some of this other stuff in order to truly sort of highlight and understand the larger topic. And then the next lecture isn't done yet, so there's some sort of we can talk about, and I'll talk with Neil about what we want, but that'll be more into sort of like the higher level study design. We'll look at more categorical data, 2x2 tables, some chi-squared and Fisher-exact testing, concepts like prevalence and incidence, odds ratios, incidence rates, adverse risk ratio, incidence rate ratio, numbers needed to treat, sensitivity, specificity, likelihood ratio, and then maybe some regression modeling, which we'll talk to you a little bit today as well, because the tests that we're going to cover today, like essentially just a t-test and ANOVA, are very, very basic. And if a study is using that as their primary means of testing their hypothesis or their inference, it's probably not that high level of study. There's obviously exceptions, and like descriptive studies do that a lot, but most studies are doing sort of regression modeling now, which is based off of ANOVAs. Like that's the core of what a regression model is, so it's important to know. So that's why it'll be important to talk about maybe a little bit next time as well.
And just to further, so before not to get overwhelmed by the number of tests we're covering, the idea of doing this at the very beginning is then there'll be a summary. So when you come across something when you're doing your journal club, you can refer back, okay? And that's the idea of recording the lecture as well. You can go in and then essentially go back to a specific topic that you're not understanding or that you might not be that familiar with, just so you have it for your reference.
Yeah. So there's various types of data when it comes to doing studies and looking at evidence. So there's continuous data, which are things like temperature, weight, whether it's the variables are continuous. There's no the difference between 2 points is actually the theoretical limit of us measuring the difference between those 2 points. Then there's discrete data where there's a more distinct difference between two data points. And these can be broken down into count data, like number of injuries per season, number of anything. Categorical data, which can then be further broken down into nominal or unordered, and this would be things like type of sport or sex, position. And then there's ordinal or ordered categorical data, which are things like answers on a Likert scale. So for example, strongly agree, neutral, disagree, strongly disagree, whereby there is an order, but the actual difference between those 2 points isn't a quantitative sum. Then there's binary data, so injury, yes or no, or even proportion, so number of individuals with, like a proportion of individuals with something is actually binary as well. And then survival data is sort of a little bit of a separate beast, which that's why I kept it separate. And a lot more studies are using survival analysis, which is like time to an event. So another thing to think about. And what's important about types of data is that essentially if you know what type of data you're dealing with, you can really narrow down the type of statistical analysis or your options that you're going to use to provide inference from the data. So moving on to descriptive statistics, very, very basic concepts here. There's only 3 things: mean, variance, and standard deviation that we want to cover. But this slide actually covers sort of one other layer, in so much that the way to calculate this is different between looking at a population statistical evaluation versus the sample, And the sample is obviously, so you have a population of individuals, and the sample is what you're collecting from and what you're using, because obviously you don't have the money or the means or the time to study a whole population, or probably the ethical implications as well. That would be challenging. So the mean, obviously the sum of all the individual data points divided by the number of individuals. The population variance is going to be the square of the difference between each individual data point and the mean divided by the number of individuals. And this is the only difference between the sample variance and the population variance, because the sample variance you actually divide by n minus 1, and that's just, it's called Bessel's correction. It just provides a more unbiased reflection of the population variance, and that's why you divide by n minus 1 for the sample. And then standard deviation is going to be the square root of the variance. So pretty straightforward. Also, these are, I mean, when you are doing stats, these are the nomenclature that they use. They use a sigma for population variance and an S for sample variance, or sigma squared, S squared. So let me keep track of it, because that's going to come up a little bit as well throughout the rest of the lecture. So very basic stuff. So the next topics that we want to talk about were bias and variability. But in order to do that, we sort of have to first talk about cumulative density functions in sampling. So we've all seen cumulative density functions before, and I'll show you an example after this slide. So a cumulative density function is essentially just a figure or a function whereby at any point A gives the probability that a continuous variable up until that point will be equal to or less than A. And what I mean by that is this. So you've seen this before. This is one particular cumulative density function. It's a normal distribution. So all it says is that if you pick any point along this, x-axis here, say for example the mean plus two standard deviations, you are able to calculate the probability of any other x value below that by looking at the area underneath this curve here. So that's what a cumulative density function is. And I bring this one up, the normal or Gaussian distribution, because this one comes up so often in biology, and when sampling data as well, it actually turns into normal distribution. So something to sort of have an idea about. A normal distribution is obviously centered around the mean, which is mu here, and tails off to the right and the left. And it's the way that you denote it is just with an n, for normal distribution, with around a mean of mu and a variance of sigma squared. One particular normal distribution is standard normal, and what standard normal is a normal distribution with a mean of 0 and a standard deviation of 1. And I bring this up because this is an important one to know, because it is essentially all the values on the x-axis are the area underneath the curve to the left and the right of that is known. So it's easy to use and figure out sort of probabilities and proportions for. So this is a popular one, 2.5%, because we often use alpha or significance value of 0.05%. So if you're doing two-tailed, it's going to be on either side, and that corresponds to a z value, which is the value on the x graph of 1.96. What's also interesting is you can convert a normal distribution that's not standard normal to standard normal by using this equation here. So any x value minus the mean divided by the standard deviation will give you your z value here. And this just says that you can approximate any standard, any normal distribution to standard normal using this equation. All right, next, so just keeping in mind the big topic we're trying to cover is bias and variability. And in order to do that, we have to look at sampling variability. So say, for example, we want to know the average weight of the football team, or an average weight of a player on the football team. You can sample players from the team. So this, for example, samples 10 players, and we do it 5 times. And you can see that the mean of our sample is actually different amongst the 5 samples, and the standard deviation is different as well. So this is called sampling variability. But what's interesting is that if you increase the number of samples that you take and the sample size amongst those samples, you actually get a normal distribution of the sampling. So this is what we call a sampling distribution. And what we find is that the mean of the sampling distribution approximates the mean of the population that you're trying to estimate from. The variance we can estimate as well using sigma squared over the sample size of each sample. And the standard deviation is going to be the square root of that. So essentially, how is this useful? This is useful because we may not know either the population mean or the population variance, but we can estimate that based on the property that the sampling distribution takes and actually turns into a normal distribution. So that's how we get to bias and variability. So bias itself, when we say bias, that relates to the mean of that sampling distribution. So this point here. A measure is called unbiased or is unbiased if the mean of that sampling distribution equals the true value of the mean from the population. Variability, on the other hand, just describes the spread of the sampling distribution, and you can reduce variability by increasing the sample size. The way that you introduce bias into a study is by confounding, and you can confound sort of at any stage in the study, whether that's something inherent to the data or the population that you're studying itself, or the way that you're collecting data, or the way that you're analyzing data that can shift the mean. So those are two important terms to know about, bias and variability. Yeah, so I think we've all seen this figure before as well.